The ideas expressed in the following presentations are those of the speakers and do not necessarily reflect the views of ACI or its committees. ACI web sessions are recorded at ACI conventions or other concrete industry events and will be made available for viewing free of charge for 1 week. Thereafter, they will be archived on the ACI website or added to ACI's online CEU program, depending on their content. You can earn continuing education credits through ACI's online CEU program. Visit www.concrete.org to register. ACI conventions provide an opportunity for networking and for keeping up to date with the latest in concrete technology and practices.
And our next speaker is Jose Restrepo, who is a professor at the University of California, San Diego. He has a research and educational interest in reinforced and pre-stressed concrete, especially in seismic design.
Good afternoon. It's my pleasure to be here and show you some of the repair work that was done in the city of Viña del Mar following the 27 February earthquake of 2010. Two of my colleagues who are authoring this presentation are here, Professor Bonelli and Professor Carvalho from the region. So for those of you who are not familiar or remember a little about the earthquake in Chile, this is the sixth largest. It used to be the fifth, but now the earthquake in Japan has cropped up. Now it's the sixth largest magnitude earthquake that is being recorded in modern times. It's a subduction type of earthquake, very similar to what we would expect to see in the Cascadia region in northwest North America. So let's see. What we have here is a very large, very wide band affected by strong shaking in the region. If we compare that to northwest North America, we'll see that it will be similar to what starting in Salem in Oregon and going all the way to Vancouver. And for those of you who do not relate this to any distance, it's about 1 hour of flight in an airliner. So all this region for about 100 kilometers has been affected by strong shaking. And obviously, when you have soft sand deposits, then you have additional amplification at the site level. The earthquake occurred in the heavily industrialized area of Chile where about 7 million people live. It is rather remarkable that only 8 people die in modern buildings in Chile. So a lot of the casualties were due to the tsunami itself or to people who were living in engineering dwellings and they collapsed. But only 8 people die in modern buildings. So that's probably something that we engineers can claim for, positive, that engineering in the end pays and adds to the safety of our communities. Having said so, we must note that there was disproportionate damage of structural damage in buildings that are relatively new in Chile, and that's something of a little bit of concern because there was extensive buckling of the reinforcing bars, crushing of the concrete in many of the walls. So it's something that you can think, in the end, we had a very large earthquake. People are okay, but is it something we could do to enhance a little, for a little cost, enhance a little the performance of these buildings? That's something that is up for grabs. So if we go back, this is a view of Viña del Mar. It's a beautiful city by the Pacific Ocean. And you see it's forested in medium-rise buildings. And these buildings in Chile, they follow more or less a typical archetype. You have a large density of thin walls everywhere. So partition, the way we do them in the United States, are practically non-existent or limited to. In residential buildings, we see reinforced concrete walls or bearing walls everywhere in the building. And these buildings are regular in height up until all the way from the top to the bottom, except at the critical level where we can see a lot of transitions and openings in the walls to give access to the parking areas. So typically we'll see slabs that are between 150 to 200 millimeters thick. They are solid slabs. They have a significant, the walls, the bearing walls have significant perforations, and they tend to be more critical near the first level where you have the accesses. So it's very difficult there to follow the load paths that you have all the way from the building. How are they going to be transferred all the way to the foundation? So it makes difficult to assess, makes difficult to capacity design these walls and really to postulate a mechanism of inelastic deformation. It could be possible, but it requires that we change a little bit the way we do these buildings. These buildings are typically found on, or have two underground floors for parking. They are generally found on mud foundations. Sometimes we have deep foundations, but they are very seldom used. So it's not common to use deep foundations in these soft soils in Chile. And next to these very large walls, we have a series of small gravity columns that can be very easily coupled by the walls and taken in tension and compression, something we fail to see in any of the analytical methods. When we are designing with elastic analysis, we just don't see, we cannot perceive that these columns are going to be coupled and they will be subjected to extensive tension and compression, for which these walls are seldom detailed for. So let me give you a little bit of background into what has been done in Chile. The codes in Chile have changed over the years, but basically the detailing remains pretty much the same. And for these kind of buildings, medium-rise buildings, the base shear is ranges between 12, 15, or something of that order, percent of the building weight. The detailing, the walls are not necessarily detailed for ductility. There was the feeling in Chile over the years that the earthquakes, the collection of earthquakes they have are high frequency, and the displacement demands are not there to push these buildings beyond the elastic limit. So somewhat the detailing of the reinforcement in many parts of these walls have been relaxed, and we can see a lot of lack of confinement, which was not required by the code, as is required here by ACI or all the codes in the world. And you see walls that have significant reinforcement at the ends with very little or no confinement at all. The transverse reinforcement for shear used to be anchored at 90 degrees. Obviously, once you have a spalling of the concrete cover, you expose this reinforcement, you lose the anchor and the bars buckle. So we saw quite a bit of buckling, which I will show you of this, and even fracturing of the bars. In Chile, the ACI code was adopted back in 1993, and it's still current today with some changes. The walls are typically thin, between a ratio between 112 to 115 of the clear height of the floor. So there are many of them, but typically they range about 200 millimeters, 8 inches, give or take some of these dimensions there. So let's now focus on Viña del Mar. It's a coastal city. Here you can see the geology of the region. You can see a lot of rock around Viña del Mar, but in Viña del Mar itself, you see is sedimentary soils. You can basically see the deposits there, the old coastline, and this is where a large number of these medium-rise buildings lie. We took for this presentation a couple of buildings. One is called Tricahue, it's a 12-story building, and Rio Petrohue, it's a 17-story building. They have the same prognosis, the same kind of damage, and were repaired with similar methods that I will show you in a minute. These two buildings are just about 2 blocks away from each other, which is nice to see and compare the difference in their repair methods or so. So let me give you a close-up of the two buildings. This is the Tricahue building and the Rio Petrohue. And you see a number of buildings. Some of them are damaged and some of them are okay. These two buildings are sitting on soft type of soils. They are typically equivalent to what we would call here in the United States ASC soil type D, low shear wave velocities, soft sands. They are founded on mud foundations. They are not sitting on piles or anything like that. A prognosis of the damage observed in these buildings was extensive crushing of the concrete at the lower levels of the building, endemic buckling and even fracture of the reinforcing steel that was quite common in many buildings, not only in Viña del Mar, but also in Santiago and Concepcion, different parts of the country. So as repair scheme, the main thing is how do you deal with the problem? Can you close some of these wall openings that are creating a lot of difficulties in the load path? Yes, you can. So you go for it, you close these wall openings. Increase the wall thickness. In some of these walls were really thin. Can you increase the wall thickness? If you allow to, you go for it. You increase those wall thickness. Can you add some walls? I mean, in some cases it is possible to add some walls, and that's one of the methods that was used in Rio Petrowe, where walls were added to add additional strength to the building. And obviously then the small pieces here of epoxy injecting the small crack widths that develop in the slabs and all throughout the height of the building. In some other applications, there have been the use of carbon fiber strips that have been applied to the walls to enhance the shear strength. So for Rio Petrowe, this is a 17-story building with a total repair cost, which does not include the repair cost on each apartment. Is all the structural repair cost of the building, the structural part, as well as the repair in the facade and the interior, the common areas of the building. So each cost associated with the repair of the apartment itself is not included in this cost. The repair cost of the building nears about $1 million, and which is about 1/3 of the total repair cost. So associated with this is you are spending a lot of money repairing things that are not structural but have to be repaired because the structure failed. And the total repair cost to replacement cost is about 1/3. If you see in Chile, it was quite common if the repair cost is nearing about 40% of the replacement cost. A decision is taken not to repair the cost, and then it's a legal process of bringing all the owners together to try to sell or form a cooperative for the building and demolish the building and build a new one. So that's a very complicated part of the story of the legal process that goes with a building that is owned by many people, and that some of them may have or may not have their own personal insurance, but the building something has to happen to this building. There are about 3 or 4 buildings in Viña del Mar that are being demolished. Some of them are still in the process of deciding what to do. This is 2 years after the earthquake. This is the kind of damage you see. The exposed here, you see the crushing of the walls in several areas. In this case, the building in this particular location has come down of the order of 1.5 inches. So you see the development of yield lines in these buildings in Chile, quite common. You can see the bars have buckled now that the concrete is crushed, and this is basically suggesting that the building has come down quite a bit. Extensive buckling and also fracture of the reinforcing steel. Very poor construction, as Des will show you a minute ago. It's also evidence in Chile, the lack of inspection and sometimes that we do some kind of sophisticated analysis and the level of construction and inspection is not there to follow up. So in the end, it gets built with very poor detailing, lap splices that do not exist. So all kind of things are exposed when you are peeling off this building and trying to see what happened to it and how you can repair it. The first thing in these buildings obviously is mapping the damage, basically try to see what has happened to the building, create a history of the damage in the building that allows you to make decisions, repair strategies, and so on. So in this case, all the damage has been mapped with photographs and dimensions and measures, and then a decision is made as to what will be the best strategy to repair the building. Here we see the mapping of the cracks in the slab. These slabs Chile is very fortunate, in my opinion, to have these thin slabs that are highly ductile. They contain the collapse of the building when you have a partial collapse in the structure. In this case, these yield lines develop in these slabs here because the walls crush about 1.5 to 2 inches, so the entire slab can redistribute the loads back to the other buildings also. One of the issues that comes in repair is now you decided to peel the reinforcement and remove the crushed concrete and expose some of these walls, but you have had creep because in these very thin walls sometimes the axial load ratio is quite high, and you remove the concrete from it, and then your cage buckles because you have had creep over the years. Your reinforcing steel has deformed elastically, and as soon as you remove the concrete, it bends. And that is not a trivial thing because you think you can pull the reinforcing the cage back into position with the mold or something. It's just not that easy. Sometimes it's easier to actually cut the reinforcing steel and overlap to overcome this problem. This is the repairs for this, just peeling the reinforcement, placing new cages. You want some walls here where you see the damage, the repair job, adding thickness to the wall, additional mesh. And the Tricahue building has a similar repair strategy. It's 12-story, 5,000 square meters, with a repair cost of $1.5 million. The structural repair cost is $600,000. So the ratio between the two of them is about 40%. So you spend 40 cents repairing the structure, and then 60 cents repairing everywhere else, restoring the facade, restoring the windows, restoring all the common areas in the building. It becomes expensive when you have to do these things. And then and for this building, the same as in our previous building, the total repair cost to the replacement cost is about 1/3. You can see the damage, again, extensive buckling, opening of the 90-degree hooks. Makes you wonder sometimes if you should spend a little bit more time in investing in detailing of these buildings and building them well. It's an extra assurance, and it will cost just a fraction of what you're spending in something else, which can be passed to the owner for a very, very modest, if minimum, additional cost. You see the damage here with extensive crushing of the concrete buckling bars, shear failures in the adjacent girders to the wall, and then the repair work, adding elements. Very similar. It's an artisan way to do the business. It's easy. The access, the spaces in these buildings are rather confined, so it's not easy to spray with Shotcrete, and it's done basically by casting the concrete and doubling into the concrete, removing, sometimes demolishing everything. This is the addition of walls, increasing the thickness of these walls. You can see one detail here where the existing wall has been doubled into to add additional elements into the wall, properly form a rectangular wall here with much wider thickness. So that's basically, it is very similar to what has been happening in Viña del Mar, in some parts of Concepción, with the traditional way of building these or repairing these buildings now that they have been damaged with the earthquake. And in this building also, there is evidence of lack of shear reinforcement common to many buildings in Chile. And I think as we learn a little bit more, we realize that the dynamic effects of buildings are interesting, and they cause larger shear force demands in some of these structures. So some of these applications, the use of carbon fibers come in very handy for restoring or providing more shear strength to these structures. So to end my presentation, I would say that in many buildings where you can assess that the cost is about 1/3 of the cost of replacement of the building, you go ahead and repair the building. In some of the cases, you have to organize the owners of the buildings in cooperatives and try to come up with decisions what to do, if demolish the building, when, how, and what to build next. It's a very lengthy and difficult process. And the repair methods have been traditional. There have been many of them, but using the traditional methods of peeling, removing the concrete, casting the concrete again, and with some exceptions where additional carbon fiber strips have been used to restore shear strength. That's pretty much from me, and thank you so much.